Hello and welcome back to the channel. It is Mark from PowerSonic and Apprentice 121. Today we're going to have a bit of a deep dive onto the main connections at the front end of your installations, and we're going to look at this from a point of view from both the consumer side and also the installer side, because it's important both ways round. We deal with this in the day job week to week, and reworking renewables kit alongside stuff that is already connected in a meter box can be really challenging. We've shared examples of that before on the channel when we've had to fit switch fuses into these areas, or when we've had customers with outdoor equipment and kit. So we've got consumer units that we're putting into an outdoor environment, and we're going to look at all of that in this video. And for you as a consumer, if you're having this stuff fitted into your home, these are among the most important areas for your electrical system. It's the place where you will come and interact and read your electricity meter, but also it's that place where the current is constantly flowing in one direction or another. There's always something going on in these places, and it's really important that those connections and the kit around them is in a nice environment. But we're going to dive into all of that. I'm going to explain it as best I can as we run through the course of this video. And for installers out there as well, we'll have the constant marketing that's thrown at us around outdoor consumer units and some of the stuff that goes on in these kind of areas. And it can become difficult to pick between what is actually required and what isn't, and I'm going to really try and set that out as best I can through the course of this video. I've got 3 specific examples of different variants of setup that we can utilize in a meter cabinet, and I'm going to run through all of those and give you an explanation along the way, including looking at some design software from Electrical OM, which really breaks down the difficulties and complexities we have around selectivity and environmental conditions of where this stuff is sited. But let's dive in and take a look at this first option I've got here to show you. So I've brought you in as close as I can to fit the meter box in its entirety in shot, and this is a typical bog standard new build home, or home from the 1960s and 70s even, where these are usually recessed into the wall, but you can also get, as we've got here, the ones that sit on the surface. And I've tried to set this up in a way that allows everybody's kit to exist. So of the past, the DNOs, so the electricity network companies, if you like, so your Northern Power Grids, UK Power Networks, SPN and all those kind of people, National Grid, Electricity Northwest, they need space for their kit to live, and this is the service head. So this is their kind of bread and butter stuff that they look after. So we need to make sure we're leaving ample space for their engineers to come and, if needed, change the service head if it goes wrong. They are the guys and girls who can't turn the power off generally, so they need a safe space to carry out the work that they're doing. And I've tried to allow for that here. There used to be a chart that was issued which showed the meter box actually quartered. I'll see if I can find an image of that and overlay it on here. Some of the DNO operators used to actually have that imprinted onto the backboard so you can physically see it. And I've tried to stick with the rough intent of that in this particular layout. And the same for the meter operators, so your Octopus Energies, your Eons, EDF and such, they need space to come and change electricity meters, install smart meters, whatever that might be. So we're trying not to take the whole box over and allow space for that. And there is argument about who actually owns this space. The DNOs say it's for their kit only and there shouldn't really be anything else in there. Homeowners argue that it's kit on their home that they've bought and it is theirs, and other people can make use of it. My own view is that there's far too much territorial nonsense around all of that, and we just need to try and work in the spaces that are available to best serve the installation in the best way we can. So looking at this from a totally new installation, I want to say how this just seems a terrible design for us all to try and work in anyway. So this is nothing like an adequate amount of space for everything that we want to do. So going forward, we need to really look at that and allow for a bigger provision of space around our incoming services, especially now as we're integrating more renewables into people's homes around heat pumps and EV charge points and solar PV and battery storage, and all of that generally needs to interact with the main service supply, that this space needs to be vastly larger. We need to be looking at cupboards and plant room areas for all this kind of stuff rather than a little meter box like this. However, we've got 50 odd million houses out there, lots of housing stock where this is a really common scenario. So I'm doing this video in the intent of sort of showing how we can make it work, difficult as it is, and share the available space as best we can to make these things safe and functional for consumers. So just to explain this then for those of you who are consumers and maybe not electricians and understand what's going on, you've got your line and neutral coming in from the electricity grid, which runs through our electricity meter, and I've retained what is called the rec switch, and this is a point of isolation for your metering companies and the DNOs if they're coming to work on any kit their side to take the system offload via this isolation point. Now my own view is that that maybe isn't necessarily required if we've got our isolation point in the kit we're fitting as electricians. However, there is some of the metering companies especially who don't like operating metallic switchgear in these environments. We'll come back to that later because the reason for it is quite interesting. So we've retained that. So that gives a point of isolation to basically cut the electricity supply off between all of this and all of this from a grid point of view. Now with this particular option I've got here, this is a consumer unit enclosure from Proteus, which allows space for a 4-pole isolator. And as you can see here, I've got a C100 MCB. We'll speak about why that is, how it is in a minute. But just to show you, those grid tails basically come in on this side here of that main switch. They then run out of the bottom side of this through our C100 breaker, and that then drops out through some steel wire armour that you can see is landed in here, and that zooms off to our gateway, which I'll show you in a moment as well, as a 5-core cable. So that takes earth, grid line and neutral to the gateway, and then returns grid line and neutral from the gateway back into the top of this 4-pole isolator. That then drops out of there in these tails to the Henley blocks, which then take the power out and away via these tails to the consumer unit. So basically this sits as a break point for the gateway for your islanding capable solar systems to have those cables connected and also form an isolation point between them. So there's always going to be the live voltages from the supply side in the top of this, so that's going to be from the grid, and that's from the backup port from the gateway, which brings the live voltage back when we're islanding. So if a consumer operates this switch expecting the power for their property to go off, it will, because all the outgoing side of this kills off the grid feed to the gateway and also isolates the consumer unit from the islanding system. Now, there's an argument for pros and cons of that. Obviously, if the switch is isolated, it might not be wanted that the customer's installation was to go off. If you was to turn this one off, for example, it would still island in the same way as designed and have voltage going to the consumer's fuse box consumer unit via the battery storage if it had a SOC level capable of delivering power in it. And we're going to look at another option later on where we utilise a switch fuse and just a 2-pole switch in here as well to account for that. But it's just a different flavour you can consider. And obviously this 4-pole switch is brown and blue, where we've obviously got a neutral in here as well. You'd want to use a different configuration in the layout of that. This was just a way of setting out this example. And equally, this 100 amp C100 amp device, we could swap that out for a fuse carrier, so it doesn't necessarily need to be an MCB, but if we were setting up in that way, I would generally just use a switch fuse anyway. They're the same sort of footprint and size, it would fit. The reason people would opt to maybe use something like an MCB is if it was to operate, it's much simpler for a consumer to reset, so they're able to do that rather than swap out a fuse. So that's often considered a more convenient form to set these systems up like. However, we have issues as an electrician called selectivity and the pollution degree rating of the switchgear and the thermal effects of being in essentially an unheated outdoor area. So with selectivity, it falls into 2 different camps. We've obviously got our DNO's fuse here, which is 100 amp rated, and we've got our C100 amp rated MCB here. Getting any selectivity between those 2 things is near impossible. It's very difficult to achieve. If that was a fuse, you would still struggle to have that. Most consumers are going to want to retain the 100 amps supply that they've got. So even if you was to drop down to an 80 amp service fuse, you're kind of limiting a little bit of the available capacity they've got on their install. So it's generally accepted that we're sort of duplicating these 2 things, and that's just kind of the way the regs works in terms of utilising the DNO's fuse for protective measures on our side. The DNO don't like us to do that. So that you do tend to see that The issue with selectivity is more towards the final circuits. So with this C100 breaker, and we'll look at this in Modexsoft Electrical OM on the graphs to explain that later in this video, but it could be if you've got a 50 amp, for example, electric boiler, that you can get crossovers in the selectivity graph. So if you have a direct fault, a short circuit fault, it's a kind of guessing game as to if this will operate or the final circuits of a current protected device. And that could be the same for your 63 amp breaker in the gateway for the PV system, for example. They will cross over. So if the cable was to be struck on the inverter battery storage system and you had a dead short line to neutral, it might be that this would operate and take out the supply to the entire install, which wouldn't be, in my opinion, very good design, because that then plunges consumer into potential darkness for a short circuit fault on a final circuit. Now obviously you could have a short circuit fault in and amongst these tails, and that would happen anyway, but that's a way less likely thing than a short circuit fault on a final circuit. And that can play a part onto your 40 amp breakers, even with your 100 amp MCBs. We're going to look at that with Electrical OM because it really will kind of set that apart and explain it. This again, you could have a steel wire armour coming in here. I've tried to set this up in a worst case example. So this is my worst case example for a meter box. We've got existing Henley blocks leading off to a consumer unit that might be living 3 meters away from here. Our gateways, you'll see we've got kind of external with our meter box just next to it. We'll have a look inside that in a minute just to explain, if you're fresh to kind of the gateway principle. And apologies if this video is going to go on quite some time. There's a lot to get through and I don't want to miss anything out. But yeah, that would kind of go off to the customer's consumer unit. If you had your steel wire armour coming in, this stuff here wouldn't necessarily be here. You'd have your steel wire arm coming in, and we'll show that with a switch fuse option later on in the video. So I think that kind of explains what we've got in this meter box, and it shows that there is space there for all of that to exist. There's ample room around the service head. We've left ample room around the meter. There is an argument as if we even need this, considering we've got that. So there's space there to achieve it. The difficulties on this particular setup for me are around the thermal effects on this C100. Now it is a pollution degree 3 product, this one, which means it's kind of okay in unheated spaces, but not in direct outdoor environments. It's a grey area with a meter box outside if that is the case. The issue I have with that, if this is operated, it's generally because there's a fault somewhere and we've got consumers coming outside the equipotential zone, potentially in inclement weather, to then start operating this. And if there's a fault on it, it might arc, it could suffer some sort of internal damage whilst it's operated, and we've just got an ordinary person doing that. They could be outside bare feet in wet weather, and I just think the risks around all of that are too high. Now obviously they could take the system off load by operating the main switch, and then in doing so we know that there wouldn't be any voltage on this particular MCB, but it's having the confidence that an ordinary person would know to do that. And that plays true if this is a fuse carrier. Obviously with a fuse carrier, there's less of a risk of them being in contact with anything arcing and falling outside of this MCB, because it is just a fuse. It tends to just go pop in the cartridge in of itself. And the carriers themselves, in fact I'll show you one, I've got one to hand here for the consumers out there who aren't familiar with these. The fuse goes in there, you operate this, pops in. It's designed to kind of hold and contain whatever might go wrong with that fuse in it. You would certainly know about it if one popped while you did that. They go with quite the bang, and you wouldn't repeat it ever again in your life, I'd like to say, as a consumer. But I make that more safe than this. Let me know what you think in the comments around that. Equally with the fuses, just to explain in terms of selectivity, your MCBs downstream of that will always generally operate when they're a B grade variety at consumer level. They usually are, and the C grades as well, to be fair, in advance of your 100 amp fuse in here. So you'll still have the duplication between those two. They're not going to achieve any selectivity. But in terms of your final circuits, if they have a short circuit fault, they're very, very, very unlikely to be affecting this in the way that they could potentially affect that. And if you drop that down to a C80, that only gets worse. C63 the same, that gap narrows. I've opted for a C100 here because that gives you the biggest gap. And like I say, we'll go into the graphs with Electrical OM later on on that. This isn't a method I would use. I'm going to show you my option when we've done this before in the past, right at the very end. But this is just one I've been playing around in my mind. I thought, we'll give it a go. It's the same footprint as the switch fuse. They're pretty much the same width. The switch fuse is a little bit higher actually, so this is a slightly smaller enclosure. But I'll show you that one later on. Said we'd have a look at the gateway, just for those of you who are unfamiliar with that. So your grid feed basically comes into your breaker here, and we do have the selectivity considerations around these. These are C125s. So these are rated higher than that C100, which tends to push them out of the hitting limits of the final circuits, which is why the manufacturers here from C Energy have got these set up as C125s. They do give you that slightly bigger gap of selectivity on your final circuits. Now there is a consideration there around the sizing of your cables due to these operating characteristics of these and the potential of seeing 125 amps flowing through your tails and steel wire armors. But that's where your max demand and other protective devices in the system play a part in allowing you to limit that. So there's a wider design consideration and discussion around that, we're not going to dwell on with this video at the moment, but it is something to be aware of. So your grid feed comes in here, then all of your inverters are brought into play to give you the capability of islanding, and your backup port runs off from that back to the little 4-pole switch in here, and then out to the consumer's installation. So if you're wanting to make an isolation for the consumer's installation, this would do it. That wouldn't do it on its own because it would still island. And then if you was to start hitting these off in the gateway, obviously that kills the power off as well to the install. As an electrician, we know how all this works, so we can safely work with it and understand what we're switching off when and where. I thought that was a good little choice, because from a consumer's side, they wouldn't know that. And that does kind of give a fail-safe from an isolation point of view. But let me know what you think. We can dive over and have a look at another option here, and this is where it gets really interesting. So this is one that we definitely wouldn't do in our installation business, but it is one that I see a lot of online without the considerations around the pollution degree side of things, and the kind of condensation and such. And we're going to touch on that now with my explanation here on this one. Now I've not got a service head on this one. I did order two, but only one turned up. The same space exists as on the last one, so it would kind of finish around here. Again, I'm trying to leave space for the DNOs, which we discussed in the first segment of this video, for them to do their stuff. We're then coming up to the meter here. And again, trying to leave space for the meter operators to do their stuff, fit smart meters, all the rest of that stuff. And again, we've retained the rec switch. Now with this one, we really didn't need to do that at all with this one, because we do have a plastic enclosure in here. Now that brings questions around the regs and the intent on metallic and plastic consumer units in domestic dwellings and all the rest of that stuff. I'm going to park that for now. We're just using this plastic box. My own personal view is if you're outside of the dwelling, there's no real issue using plastic, because if it was to ignite, it's outside and it's not going to cause any issues and such. So I'm happy enough with that, but why the conversation? Now the same thing exists here, where the grid power comes into the top of our rec isolator. We then drop out of our rec isolator into this main switch here. Now this particular setup hasn't got any solar battery storage on it. This is just your sort of atypical consumer's system, where we're maybe looking to integrate an air source heat pump or an EV charge point, and the methods that lots of people have been pushed towards now are outdoor consumer units. We're now having that explained has been an option of last resort, and we're seeing some innovation from installers and kit manufacturers around starting to look towards siting this stuff in a meter box. Now for me, final circuits we shouldn't really be putting in a meter box or an outdoor consumer unit. I know that there's actually estates full of consumer units in meter boxes that were done in like the 70s, I think, where they were just put in there. So the meter box had your meter and such, and there's also like a space for your consumer unit. And these are on the side of bungalows, new build homes and such that were done of that era. And obviously you've got your skeleton boards and such in flats and high-rise buildings where the switchgear and stuff is housed in those with the metering kit. So it is not something new. This has kind of gone on for a long old while. But like I say, we formed the view in our business that we're not happy doing it, so we wouldn't. But if you were to, I just want to point out some of the things you need to consider. So again, we drop our grid feed in here. We've then got this D63, which again comes back to the selectivity issues. You're definitely going to see an issue between the main service fuse and that. and you were going to see an issue on your final circuit. Certainly 40 amp B40 breakers will overlap with that. Some people think just dropping down a value gives you enough selectivity. Again, there's videos on my channel where I've actually shown with fuses in series to each other which ones pop first, and the same with MCBs and fuses, and it's quite interesting to see how they actually behave. And when you only got partial selectivity, it very much can be, with a dead short, the best guess as to what operates. But that can feed your consumer unit, and you can see that then pops up through this brown tail here into our pink Henleys. These should be brown and blue, but we ran out, so we've got pink, which is functional F, by the way, for those of you who are interested. But same principle as on the last board I showed you. The line goes into there, the neutral taps off this neutral bar here, and is returned up to there as well to go to the consumer's consumer unit. So they can have the consumer unit in the house looking after all the final circuits in there, and it's powered from this here. So that still gives us a single point of isolation, which is why we set it up like that. We've then been able to maybe lose this and create some more space in the meter box. In setting it up like that, it enabled that to be a thing. We've then got our SPD, really close to the source, again, bus bar mounted. I know there's a discussion around in industry at the moment as if they need MCBs or not. We'll park that for the moment as well. This one doesn't, it's just sat on the bus bar, as designed from Proteus. You can fit it anywhere you want on that bus bar, and it will look after your transient surges out from the grid coming into your installation. We've then got a B32 here, and that could be for your heat pump or an EV charge point. It could be B40 rated, whatever you need. And that will allow you to connect a final circuit from this location. And you can see we've got some EV Ultra actually that drops out of here. So that's got your comms cable in for the CT that might need to go onto some of this. Be a tight old squeeze, but you could do that. You could even house the CT out of here and have it pass through and be wired into the cat cable in there. And then we've obviously got our power leading off to whatever the kit is doing its thing. This last little circuit here is looking after our heater. Now this is one of the considerations with this. This switchgear is pollution degree 2 rated, which means it's for indoor environments that are heated. So it's not an unheated space. It needs to be an indoor environment where you're going to have reasonably settled conditions. Now we have got our IP enclosure, which does have a lid on it. In fact, I'll show you that, which allows for sort of protection from dust and elements and whatnot of the switchgear itself, which is why I've selected this particular board. So you can see it's got that plastic cover on there. It seals with a weather seal on there. So there's going to be no dust and moisture in normal operating conditions reaching any of that. So it's trying to keep it as a stable environment as we possibly can for that pollution degree 2. Now, if this was a little bit larger, you could even consider putting the heater inside this box just to try and stop it dropping to a level where you're going to see condensation forming, and the colder temperatures affect how these tripping characteristics of these devices behave. So basically, the colder it gets, the more current needs to flow before it will trip for an overload, basically. So that can bring into question the protection on your cables, and our protected devices are always primarily, well, mainly looking after the cables. We're trying to stop them overheating and setting fire and whatnot. When it gets warm in this box, they become the opposite of that, more sensitive. So you can see what is termed nuisance tripping, where it could be, if this is a B32 for example, it's very close to its operating limit with a 7.4 kilowatt EV charger, and in warm weather that might drop it down enough to start tripping off from time to time when it's been running for a prolonged duration especially. So that's something else you need to think about, and that's where ventilation can play a part, so fans and such. These boxes just aren't big enough for that, and they kind of are generally not put on south facing walls. They're white, so they reflect the heat away. There's adequate ventilation on them. These aren't a weather sealed door, so they do allow air and such to come in and flow around. So I think in terms of ventilation, naturally aspirated is as good as you're going to get with that. This particular thing here, we've set to, in this case, about 2 degrees Celsius. So as the temperature hits 2 degrees Celsius, it triggers this little heater. Now that could be a larger heater. You can get tube heaters that would maybe fit on the side here or over here or across the top. There are ones in the size footprint that would fit. This is a little 40 watt heater. I think the tube heaters of that size are around 60 odd watts. That's about as much heating as you're going to get in this space, I would say. Of course, you could double them up, try and fit another one in as well. At the end of the day, the space and size it is, if it's -5 outside, keeping that above 0 is going to be quite a challenge, but not impossible. And again, we're trying to control the elements in this box as best we can to make this as much like a pollution degree 2 zone as we can, and also try and control a little bit the lowest temperatures these devices might be operating in. And we're doing that to try and stop condensation forming on the terminals. We've been out to lots of these outdoor consumer units that we've looked at where other people have fitted them, and they've been corroded away inside, and it's not water getting in, it's condensation forming in the box due to the overcurrent protected devices running warm. EV charge points run for 7 hours sometimes towards the wax breaking of the protected device, generates heat, cold ambient weather around it with high humidity. That moisture is then drawn into these enclosures, forms as condensation on the terminals, and we see that damage the kit. And usually it's due to the fixings going through the back, allowing a not full airtight weather seal IP65 sort of situation, or the glands maybe not doing that either. It's really difficult to retain that IP65, 66, 67 rating once you're making penetrations into these boxes in outdoor areas. Very, very difficult, and you will always see that humidity in the air being drawn inside these enclosures and forming, and that's where you get your problems with this kind of stuff. But it is a way to try and show you can include a heater in this space and fight against it as best you can. Show you've made an effort to consider it, try and stop it. This still does fall back into a place I don't like due to consumers coming to operate these, and there's an argument there about the other meter cabinets I explained earlier in the video that have been like this forever, where they're going outside the potential zone in potentially inclement weather, and regardless of this having a weather front on it or not, they need to open that to gain access to start resetting these when they've tripped. They will usually have tripped because there's a fault state at play. We don't know what that fault state might be. They could be out barefoot, stressed and rushing, trying to get power on, banging these up and down with faults on the spinal circuits, pollution degree 2 kit in an environment it's not supposed to be, exposing themselves to unnecessary danger. And it might also be that it's pitch black and they're out there doing it. It's just really poor design, in my opinion. But it does cover off the angle that you've got a metal box with all the metal parts, no RCD protection on your tails leading into it. So if this is an outdoor consumer unit, for example, typically that supply is brought off one of these into an outdoor consumer unit, which is just directly on the wall outside. It's metal, there's no RCD protection on it. It could be that there's a potential pen fault that's forced the EV charge point to shut down. The consumer's seen that, they need to get charge in the car to go out. What's going on? They don't fully understand what a pen fault means, so they come outside and they start resetting these. That metal box is on an outside wall, outside the equipotential zone. They're touching it. There could be a pen fault on it because the EV charge is tripped because there is an actual pen fault. And the consequences of that are awful, which is one of the reasons I think we should not be doing that with metal switchgear whatsoever. However, that is the direction of travel we've gone down. Much better with a plastic one, so at least if they're operating that, there's no metal parts and they're insulated from it. It's the lesser of two evils, in my opinion. And equally, if you are going to use a metal box outside for anything else, you would need RCD protection on it. I know pen faults don't trip RCDs, but your earth faults very much do. And again, it could be that the EV charge point's tripped due to an earth fault, which is then returned onto this kit. If the original installer hasn't used, for example, a double pole RCBO, sometimes is the case, and that neutral earth connection builds onto the metallic parts of the case, and you have a problem for a consumer coming to interact with it. So I just want to try and explain that one and show an example. I hope that makes sense. Grid power coming in, no renewables on this one, grid power flowing out to the customer's consumer unit, and basically just some spare ways here to put some vinyl circuits on, EV, air source heat pump and such, and for it to sit and live in the meter box, leaving space for the DNO service head and also the electricity meters kit. And as we said right at the start of this video, it is a terrible design to consider as a concept from new right now. We need much bigger spaces, so we don't have this kind of nonsense going on for the future. This is really just to rework into existing spaces where stuff has maybe been done that we don't like, and that could be coming across a very bad attempt at fitting an EV charger supply from somewhere like this that we want to rework in a better way. The options of last resort, as Craig O'Neill at the IET termed it in his article around outdoor consumer units, is such a good definition of this. It's something we don't want to be doing, but if there really is no other alternative, we need some tools in the box to draw down into to help resolve it, and I'm trying to offer some of those in this video. We'll go and look at the final one right now. So I've got you this last example here, and this is with a traditional switch fuse that we've adapted to account for this one again having a backup gateway function. So very similar to the first version that we shared, but obviously that had an MCB in there rather than the switch fuse. We've also removed the Henley blocks that were up here and popped in a sub-main of steel wire armour variety, just to again show that that can be done. Now this is a taller box than the consumer unit that was there before with the MCB in, so it's a little bit high. We've got even less room at the top here. So it is a tight squeeze, certainly whilst retaining the rec switch, but it does go. I've moved this as far along this way as I could. It was sort of sighted here, but I thought I'd try and demonstrate how, you know, you can swing it right over and free up as much space as possible over here for the DNO and the metering company. So this is now running off to a consumer unit that would be remote from the meter cabinet, and that's very typical in a new build kind of setup, where it could be in the middle of the house under the stairs and this is on the external wall. So it's not uncommon to come across a meter cabinet where the steel wire arm comes into it, and they've used what's called a Tembi clamp, which is traditionally used in a lamppost to separate out the cores of the steel wire armour and earth the armourings. Now in doing that, generally is what's done is these single insulated cables you can see inside here are left outside of the enclosures. That brings a potential for risk again to ordinary persons who are accessing these spaces to read electricity meters, and also those people going to work on the kit. So it could be the DNO operators, the metering installers, and those single cables through the course of those work could put them in danger and also potentially result in them being damaged while those work activities are carried out. Way better, in my opinion, to have the secondary layer of insulation on those cables. It's just a bit of reinforced knowledge, if you like, that any consumers coming into these areas aren't going to be exposing themselves to any unnecessary risk, and those of us going to work in them have a reasonable chance of being able to work safely as well. The other thing to bear in mind with all of that is you can't isolate this enclosure without first opening it. So whichever way around you do it, those single insulated cables are always going to be there even while you're operating the switches and stuff. It's something that's so easy to avoid. I don't think we should have ever been doing that. But that is one of the things that developed. So the new build developers, designers, were kind of putting that as the de facto approach. The steel wire armour came in, it broke out, and sometimes it would go straight through a rec switch like this. If you were lucky, they might have a C63 double pole MCB that they'd used with some form of enclosure to try and connect in the steel wire armours, and then the tails leading off from it. So if you imagine this switch fuse not being here and just a simple switch like this with a small enclosure, tails coming into it, and then the steel wire armour cables leading off out to it to the end consumer unit. And we're coming into the installation then to try and make good of that. We wouldn't want to leave it as it was anyway. We would certainly be looking to gland the steel wire armour into some sort of enclosure. That could be an adaptable box maybe to then wire through. I've seen efforts of that from others, and you know, it's a legitimate approach when you're trying to make good on an existing cable in this area. The other difficulty is that steel wire armour cable will generally be very rigid and not have a lot of play in it because it's fixed into the fabric of the building. You can't bend it, move it, you certainly can't make it any longer, and you're kind of working with what you've got without reworking the whole cable back to the consumer unit again, or taking the customer's house apart to try and find a place inside where you can join into it with some tails or whatever. It's not easy, and this is a way of getting around it. And again, I've shared on the channel before when we've done exactly this with this exact switch fuse. In that example, the steel wire armour was even more difficult because it entered from the back, I want to say, and we couldn't get the bending radius on it to get into the switch fuse whilst keeping it on the backboard. So we actually had to take an approach that you will see the DNOs doing, where they fit a sort of angled piece of timber here to fit their service heads on. And that's when they have the same problem, bringing their main supply cable into the head. They need a bit of an angle on there. We did the same by just setting this forward ever so slightly. It did bring it to the front of the enclosure. Again, it wasn't something we really want to have had to have done, but it was the only thing we could think to do in the circumstances to make it work. But yeah, just to explain this one again, so we've got the grid power coming in through our rec switch, which is a point of isolation for those metering guys and girls again. We're bringing the power into our main switch here. This then comes out of the main switch for the neutral, which runs off to our gateway. The live pops up through the fuse to give us the fuse protection on our sub-main to the gateway, and that then takes that live feed to it. The cable then returns power back into these two 100 amp connector blocks you can see on the DIN rail here at the outer extremities, and that then takes power line and neutral, which is off the backup port on the gateway, through the existing steel wire armour back to the consumer's installation. We don't have the 4-pole isolator on here, so if this or that is operated, it essentially cuts the connection between the grid cabling and the installation cabling. But obviously if the system is island capable, you could still have voltages flowing back through to the consumer unit unless isolations are made in the gateway, as we showed earlier before. Now the beauty of this is in terms of selectivity, really. This is why if I'm doing rework in a meter cabinet, I'm going to be looking towards this. And you can get smaller switch fuses. The reason I've gone for this one, it is the biggest on the market from Proteus. It's the largest consumer unit that's sold. Switch fuse that's sold. It's just to allow space for these, basically. Otherwise, you've not got much prospect of fitting everything together. There's barely enough room in a normal switch fuse to get your main tails in and out of. Never mind glanding a steel wire armour at the top. This other one down here at the bottom, and then break out those connections as well. It's not easy. So that is why I've gone for this one. It does take up more room in the meter cabinet, but for the greater good again, I would say. Again, we've got our DNO earth coming into the earth bar in the switch fuse. That earth then takes earth off through the steel wire armour to the consumer unit, same with the armourings, and then likewise out to the gateway and the armourings also with these piranha nuts onto the casing. So we've got really good earth paths and continuity between stuff. One of the things I don't like is where we use bolted connections carrying the main earth through to the final circuits, the distribution circuit to the consumer unit or onto our gateways. It's just, I don't like doing that for the main point of earth. It's one of those which is open to opinion. Typically with your roofing nuts and bolts, definitely not. But if you were going to do it, then use brass. It just allows for a bit more resistance to corrosion, and you haven't got the mixed metals and stuff. It's one of the reasons I prefer to get the earths into a terminal bar. You know, all the metals and screws have been designed for that purpose, and when you torque and tighten them down, they're going to stay where they should be. So I much prefer to do that where we can. This gives us selectivity to the final circuit, as we discussed before with our fuse. So any of our final circuits are very unlikely, as near on impossible, to be operating that when they have a short circuit fault. But obviously we don't have selectivity again between there and there. That's the nature of the beast. If we drop down to 80, we get a little bit of partial selectivity. I think the graphs ever so slightly overlap. Fuses do give you a much better prospect of getting selectivity between devices. So 80 to 100, you might actually have enough of a gap on the curve. And again, we'll look on electrical OM to see for that not to be an issue, but same sort of problem. Customers with air source heat pumps, EV chargers, battery storage systems, they want those things to be filling up in the same slots overnight, which generally means you need the full allocation of 100 amps due to the duration they're running and the thermal effect through an 80 amp fuse. If it's there, they're going to want to use it. And the problem's amplified when the DNO only gives an 80 amp supply, and if we're fusing down again, we're in the realms of a 60 amp, becomes even more difficult. So it's one of those where the selectivity between those two things isn't generally achieved, and it's kind of turned a blind eye towards, because then both, if one or the other operates, it's the same consequence at the end of the day. It's a bit more difficult to get the DNO out to come and swap your fuse, but they will do it. So it's one of those where you don't want it to be happening, but if it did, wherever it's gone, the same result applies. It's just that demarcation in overcurrent protected devices. If the DNOs were happy for us to use this in our sub-main leading off to a gateway, we wouldn't necessarily have to have this. They're not, so we do. The other point of note with this is some installers have before, where we bring in our gateway supply back, we can break apart in here, and rather than connect them through these 100 amp blocks, I've seen it where it's brought out the top in some trunking, for example, and then you can put Henleys onto the trunking. In fact, we've done that on one of the GRP boxes we fitted next to an existing meter box. There was just no room in that to fit this the way it had been set up with the meter and head. It was never going to work. And we did that. We put a length of trunking up the side, sat Henleys 100 amp connector blocks off the trunking, brought the steel wire armour into the trunking, glanded it appropriately through it, and then subdivided everything out of the kind of trunking into Henleys. So you can do that. That is another option if you want to avoid having kind of connections. Every connection point is a potential point of failure, and I guess if you can do away with these two here, you know, there's an upside to that. One of the things I would say is, and I've seen this done before again, is coming out of kind of a stuffing gland and retaining these single insulated cores but making an effort for them not to be single insulated by pushing these outer sheaths over. And while technically that does give it the insulated and sheathed classification that you have with your tails and such, it's not been manufactured as a product by a manufacturer. You've kind of self-made it, if that makes sense. So you become the designer responsible for that cable. So it's up to you if you want to do that. There is an argument that, you know, it satisfies the intent of our wiring rig. It is insulated and sheathed, but you pop that sheath over the top. Is it going to stay where it should? Does it fit appropriately around the inner conductor and its insulating material? I don't really want to give a view on if that's okay or not. It comes down to workmanship, I would say. But that's an option as well, where you can do away with these. Just wanted to pop that in there. With these, again, the thermal and environmental effects, the fuses are fine in pollution degree 3 and 4. It just becomes an issue around when they've been replaced. And again, you're out in the elements, in the wind and rain and whatnot, and you might need to be doing that. But of course, because we've got the selectivity separation on our final circuits, it's unlikely that this will have operated on a short circuit fault before any of those. So in these operating, it's going to be a consistent overload from your maximum demand. So if your dynamic load limiting's failed, for example, on the inverters and EVs, and all of this has led to a massive draw of current that's popped it, that could do it. It could also be potentially when you have a fault on some of these tails. Again, it's really unlikely if they're all glanded, secured, terminated adequately. We're not leaving any metal parts exposed any more than they need to be. It's unlikely that they're ever going to develop a direct short with each other. I suppose if there'd been an overheating effect on a termination that could maybe melt stuff and cause some arcing and tracking between the two, but potentially you might see that where you've got a fault state that has actually blown the fuse rather than an overload. The difficulty is with an overload, when the fuse pops, that kind of load's taken away, all the kit shuts down. Once the fuse is restored and put back in, it's unlikely to trip immediately again. The load would have to rebuild and that fault represent. With a short circuit fault, if something's gone wrong in the wiring system, when you swap the fuse and then pop that back in, it's going to go bang and scare the bejesus out of somebody. Of course, if you turn the isolation switch off, that will remove that from being a prospect until the switch is re-energized, as opposed to when the fuse is pushed in. But it's a factor to consider. These are all the things that play a part in your design considerations, and because these are outside the equipotential zone, because ordinary persons will go and interact with them, either reading meters through the normal activity of that or messing about resetting breakers and whatnot, I don't really think we should be doing it anywhere beyond just a basic switch fuse to work with a submain to a consumer unit inside someone's house. But they're the options. Make of them as you will.
So I thought we'd have a look on electrical OM and see some of the issues that we might have around selectivity, in particular between our overcurrent protective devices. And you can see here on my supply, we've got a ZE present, and we've also got our fault current that's present as well. We've also got our tails that lead off to the meter cabinet DB, which is going to be the switch fuse or the consumer unit or whatever we've put in there. And then that goes off to our gateway. There's a couple of circuits off the gateway, one to the inverter, so in this case the Sargent store, and then we've got another circuit which leads off to the house consumer unit. And this allows us to play around with things a little bit and see where we might get some crossovers. So you can see to begin with, we've got our 100 amp service fuse. We then drop down to our 60 amp fuse in the switch fuse in the meter box. And then we've got our gateway, which has our 125 amp breaker in here. And then the 63 amp breaker going off to the inverter, and then some final circuits that I've popped in as well. So if we're going to circuit edit on the EVSE circuit and we click selectivity, we can see that the EVSE has no crossovers anywhere on any of these graphs. So that is free from any issues with selectivity, but some of the others are very much crossed over. So if we look at the 100 amp main service fuse to our 125 amp breaker in the gateway, they're very much overlapped. It's really difficult at a single phase level when you do have a switch fuse and other breakers in the mix to ever get full selectivity. If we look between our 100 amp fuse and our 60 amp fuse, you can see that they're living separately from each other. So they do have that. So if there was a short circuit fault at 60 amps, you should see that fuse in the meter cabinet consumer unit operate before the service fuse. Is what might not be guaranteed is if you've got this 125 amp type C in the gateway, that could very much operate in place of either or of those. So if we zoom in and have a look at that graph, you can see it's just touching the 60 amp one. There is a little gap there, but it's very, very close still. It's closer than I would like them to exist to each other, but that's the nature of the beast with those things. So if we go back into the schematic again, and we can start to move around some of these. So obviously our service fuse is fixed. But what happens if this fuse in the switch fuse in the meter box is changed to, say, an 80 amp, another common fuse size that we might have in our system? Again, we'll map it to the same fuse as what the service fuses like to be using. And you can see it's popped up a selectivity warning straight away. And that is giving us a gap on here between those two. So it's not to the service fuse. But if we look at our EVSE again, let's bring that final circuit in. It's not to that, but we've got a clear crossover between the 125 amp and that 80 amp. It's brought it right into the same window. Basically, it covers and clashes with those. So that's where we're getting that problem. And that's a forewarning to using MCBs in general for your main overcurrent protective device. And we'll come back to that in a little segment of the video later on, and in this little clip as well. We'll have another look at that. But what's to say if we was potentially to swap this fuse for an MCB, as we're kind of demonstrating in this video? So we swap that out. We're not going to use a fuse in our little meter box distribution board anymore. We're going to swap and use an MCB. And we'll start with a Type C 100 amp. You can see we've got that selectivity warning that's popped up again straight away. So if we go in and look at that, we've got our main 100 amp service fuse, and you can see we've got that crossover again with our 100 amp MCB. So there's no guarantee there. Like I say, it's really difficult to get that separation anyway. And that's something that you're going to have to live with on most of your setups, whichever way around you approach it. Very, very difficult to avoid in full. If we look at the EVSE again, that's still showing as clear, but we've got all these crossovers now. So our 125 amp gateway Type C is crossed over with our 100 amp, and it is also crossed over with our service fuse. So we're getting lots of selectivity issues there. And what that means is if you get a direct short circuit fault, you could see any of those operating. Basically, there's no guarantee one would go before the other. So if the tails leading into or out of the switch fuse that we've got in the meter box was to have a direct short, there's no guarantee as to what might go there. Or in the gateway, even if you get a fault at the end of that, if the MCB in your distribution board in the meter box operates before your service fuse, it's really difficult to be able to tell. And if we look at, say, the ZAP boiler, we'll bring that one in. This is where it's interesting, because this brings in a 50 amp circuit. And you can see that then starts to touch in on some of these other breakers. We've got a really small overlap just in here. So that is actually giving us a problem to that 100 amp Type C. So it's not just with the service fuse. So in this kind of problem here, if, say, the Zaptec boiler goes wrong, or any electric boiler or an electric shower, and you have a direct short and it was to try and operate its own MCB, you've got a reasonable prospect that that would go before your 100 amp Type C at the origin in that meter box consumer unit, but not a guarantee. And I've shared videos on the YouTube channel a few years ago where I've actually done experiments of different fuse wires, different fuses, different MCBs, putting dead shorts onto the circuits and seeing which ones go. And the results were varied. It just depended, really. There was no rhyme or reason to it. And that's very much how it plays out when you haven't got full selectivity. So the risk with that kind of setup when you are using an MCB at source is if you have a short circuit fault in one of your final circuits, you can potentially lose power to the entire installation. Whereas if you have a fuse, so switch fuse at that origin, you are much less likely for that to be an issue, because you do see those gaps in the selectivity graphs between your final circuit overcurrent protected devices and the fuses. And you can see that here for the 100 amp fuse that we've got on the main service head. If we compare that down with there's a 50 amp circuit for the electric water boiler, there is spacing between those two. So if that's what you had, your 100 amp fuses, you know that if you get a dead short on that final circuit, it's going to trip the breaker and not take out your main supply, which is something I think is important. I'm less worried about selectivity between the service fuse and whatever fuse we might have in our switch fuse. That's just the nature of kind of demarcation between the DNO's kit and our own. For me, I think getting that is really very difficult when we're subdividing in the way we are with gateways and whatnot. But setting up in a way that you don't have an issue with a short circuit fault wiping out your entire power through your system, I think makes a lot of sense. And if we go back to that schematic again, because some people might try and get an element of selectivity between the 100 amp service fuse by, say, opting to use an MCB that's rated to 80 amps, for example. So it could be that you've got a Type C 80 amp MCB, and you could even go up to, say, having a 20 kA rated variation. The one that we've got in our example is very much of that ilk. So we've gone for one of the industrial grade MCBs primarily to offer some assistance with the pollution degree rating. But they do have differences again. So you can see there we've got that 80 amp MCB. And if we go back into the selectivity study, make sure we save our changes, you can see between that 80 amp MCB and the service fuse, we've still got that problem as we would expect. And if we look at the Zaptec again, so we bring that boiler in again, it's because it's a higher rated breaker. That's where you get these crossovers. We look at that graph again, it is crossing over quite substantially more this time into the graph here. So it has got separation out to the 125 amp gateway MCB. It is clear of that one. But if we look towards this here, this is where we've got that crossover between our 50 amp breaker and our 80 amp breaker. So there's a possibility that on a direct short, so short circuit fault, that the 80 amp breaker could be operated pre the 51. It's unlikely still because it is a literal corner of crossover, but it's a possibility. And for me, I make that poor design knowing that and setting out for a consumer where they might have their whole home plunged into darkness if something's gone wrong. For me, I think there's things we can do to stop that from being an issue. And that's one of the reasons why I try and avoid the MCBs at source with our main switch fuses. We do have the problem in the gateways because they obviously have the MCBs on the grid inputs and the backup out from that. And the manufacturers try and allow for headroom with that by rating to 125 amps, certainly in the SIG energy ecosystem. And it's harder to get your overcurrent protection for your tails without upsizing them in that case. Of course, you've still got your service fuse and your maximum demand calculations that can come in and play a part. So it's not a finite science with that, but it does mean you need to consider it with your cable CCAs that you're selecting into your gateways. And there's kind of a wrestling point in your design with that. Now, if we were to have those MCBs as 100 amp rated, so say we've got a different gateway manufacturer, Give Energy and Tesla approach it in a different way, for example, and the Give Energy you can choose. Sorry, the Tesla you can choose your own, and I think the Give Energies, I think they're rated to 100 amps. I'd have to go and look. It's a while since I've had my head in a gateway from those guys, but we'll jump back and change that. So if we go into the gateway here, and if we have a look at our house consumer unit protective device, and we'll change that to a 100 amp rated breaker, just to give that view again. So if we go and look in the selectivity graph now between the generic fuse, so your service head fuse, and then to that 100 amp MCB, you can see there's very much a crossover. And then we've got our 80 amp MCB again that is in the meter cabinet board. There's a crossover there. And what we're really looking for is any kind of interaction between that 100 amp MCB that might be living in the gateway and our final circuit. So if we bring the ZAP boiler in again, and the one we're looking for is an overlap between these two, and you can see there is. So this is where it gets a bit closer with those things again. So we've got our 100 amp breaker that we've put in the gateway there, and we've got our Zaptec boiler there, and it is just touching, looks just inside it. So it's this red graph or maroon coloured graph here and the green one. So we've got that little corner just creeping in there, which gives you the potential for, if you have a short circuit fault on this electric boiler, of subsequently operating your gateway's main 100 amp breaker. So I think if you were to approach it from the point of view of fitting an MCB at the source or with the gateways, 100 amps is the bare minimum of what I would be looking to utilise, just because some of the final circuits now are so high powered. It could be a heat pump, electric boiler, stuff like that. Even your induction hobs and things, some of those can end up with quite large current that's needed, and as such, large overcurrent protective devices. And if you had a potential short circuit on those, you could bring into risk that main protective device tripping. The setup that I think works best in this case, we'll end on that one. We'll put it back to how it is with the SIG Energy kit and what I think the approach I would use most likely would be. And we'll pop it back to a fuse in that. Sorry, this is the gateway, isn't it? So we'll go back to our, no, it's not. Pop the 100 amp fuse in our meter box. Just check, I haven't got mixed up there. So yeah, we've got our 100 amp leading out of our meter cabinet distribution board, and that's a fuse. So we need a fuse carrier in there. Switch fuse basically leads off to our gateway. We then need to change the gateway's power supply to the house consumer unit again. So we go into our protected device and we change that back to the 125 amps. Make sure we apply those changes. Have a look at our schematic again. I always find it easier to work around Modexsoft in that way. And we've got those on there now, so we can go back into the circuit edit function, have a look at the ZAP boiler, and you can see that's now got no selectivity issues. So we're clear on that. The selectivity problem we've got, again, is between the main service fuse and our generic fuse that's in the meter cabinet switch fuse. They're exactly the same. They're not going to have any selectivity between them. And then we've got our MCB in the gateway, which also overlaps with those. So any kind of short circuit around your main intake and your tails, there is a close call into what would go and when. The more likely thing where you're going to have a short circuit fault is in your final circuits. And if we know a 50 amp type B is clear of them, then we're very likely to have full selectivity from our main incoming overcurrent protected devices. So the DNO service fuse, the fuse in our switch fuse, and the gateway's MCB with that setup. We're not going to get it between those three, but we'll get it between everything else. And if we look at the EVSE again, that's a 40 amp breaker, and you can see that has shifted further away. Now, if we was to change the Zaptec boiler to be, say, a C type instead of a B type, that changes things ever so slightly. And you can see we then would have a problem with the selectivity crossing over, and it's doing it. We look at that there, it's crossing over into the 125 amp MCB. It's still just about clear of the fuses. It might actually just be nipping in. Now, I think it's just on the edge there, so we've avoided it with those, but we are into a crossover with this one here. And that's where you need to think about the use of C and D types in your final circuits. It does make things even more tricky with selectivity. And again, if we were to swap over to a type D, just to show you how that would play out. So a 50 amp type D, which is pretty much the worst case you're going to have in a domestic setting for your maximum sort of breaker sizes. We go into that selectivity study. We can see our type D there has kicked right over, and that now crosses across the MCB, and it's also hitting into the DNO fuse and our main service fuse as well. So if you're using D types in your final circuits on a dead short, you do have the potential to wipe out any of your supplies as well. So that tends to be why at domestic level, sticking with your type Bs is a better play with that. But I just thought it'd be interesting to have a little look through the Modexsoft Electrical OM, visualize that selectivity problem I've been talking about. I still think we have a bigger issue around operating MCBs. We know that it's likely they may have tripped due to some water ingress to an EV charger, or frustrated consumers gone to their outdoor consumer unit to reset that with wet hands on a piece of kit that isn't pollution degree 3 or 4, it's just 2. And then in doing that, well, they're out in the rain on the massive earth outside the potential zone. I think that is a really, really poor approach. And the same can be said if you've got an 80 or 100 amp MCB in a switch fuse or a consumer unit in your meter box that is just feeding power off to the house consumer unit or the gateway, that a similar sort of thing could have happened. It may be that you've had a fault with your electric boiler that's led to it tripping. The customer goes out in inclement weather, starts resetting those, even if it's a pollution degree 3 breaker, which is a bit more resistant to that moisture, dust, and you're less likely to get arcing and bangs through the front of the MCB, through a person. I still think there's an element of risk there that is avoidable, and I wouldn't be wanting to do it, which is why using fuses makes sense, because then it's really unlikely that they're going to trip on a short circuit fault with your final circuits. And if they do, there's the main switch to open up first before the fuse carrier is opened, change your fuse and such, put it back in and use your main switch. It's a little bit safer, in my opinion. It's still not fantastic, but it's a better of all of the available options, I would say. But that's more something to review down at the meter box. So we'll go and have a look at that and close out this video there.
So I hope you found that an interesting run through some of the things you can consider in a meter cabinet. And again, I've tried to set this out in a way that considers most of the design issues we have when we're faced with this kind of problem, and also some of the scenarios that might develop if everyday consumers coming to use this. And all I would say is if you're an installer thinking about outdoor consumer units and putting switchgear in the meter cabinets, just take that on board and form your own view. And if you're a consumer and you have got an installer who's kind of pressing you to have an outdoor consumer unit fitted or putting stuff in the meter cabinet, ask them to validate the reason for that. Is it an option of last resort? Could we do something different? And explain to them your concerns, if you have them like I do, around operating switchgear out and amongst the elements. You know, you could consider putting a shelter over the meter box and such, like we would when the gateways are sited outdoors in a similar kind of circumstance when it's an option of last resort. We're told to actually shelter those, so then that's keeping driving rain and weather off them, and there's some sort of prospect of them being a safe environment. And of course with a gateway, we generally will have an earth electrode for the islanding side of things, so we're covering off a large degree of problems to do with pen faults. And there is that shall and should in the regulations, so it's a should really with a PME TNS supply that we're fitting earth electrodes on our projects anyway, which again can reduce the risk from those pen faults and things with metal work outdoors. But again, that's something that's ignored by a lot of electricians because it's not a shall, it's considered more optional. But when you look at the word should in context, we should maybe be doing that a little bit more often. We certainly have no choice when these are going in. If you've got any questions around this video, as always, please do drop them in below. It'd be great to see your views around all this. If you've got some other ideas and suggestions of stuff that can be done, please also chuck them in there. I've seen the guys at eFix sharing some of their views and solutions to these kind of problems as well, where they've used an aluminium adaptable box and terminated the steel wire armor directly into that, and then used like a rec switch of sorts, which is a bit wider than the one we've got up here and allows for an MCB, SPD and such to be fitted in there. In fact, I suggested that as a design proposal to Proteus maybe a year ago. So it was interesting to see that those guys have been thinking along similar lines to myself. In the end, I decided encouraging people to kind of fit stuff in these places maybe wasn't the best approach, so I never really pushed forward with that. But yeah, it is another way you can do it, so go and check the video off from the guys at eFix. I'll drop a link in the description to theirs. I'm sure you'll have seen it already anyway if you're watching this one. Thank you very much for taking the time to take all this in. I appreciate it's been a very long video, and otherwise we will see you on the next one.